Okay, hi everyone. So it's Saturday night, which means that it's the update of the weekly paper. So okay, so this week we let's study this paper, Teaching RF to sense without RF training measurements. By Hong Shuai in University of California, Santa Barbara. Before that, I have actually collected papers that I read and I organized them into this GitHub repo. Feel free to feel free to read and also leave some comments if you like. Okay, let's go to this paper. So actually, it's published in IMWUT 2020. So actually, the title is a little bit exaggerated, and I would like to say teaching RF descent without real RF training measurement, because they do use RF measurements for training a new neural network, although they're captured in simulations. So I think the authors want to emphasize the fact that these RF measurements are not collected in the real world. So the reason why I chose this paper is mainly inspired by some recent papers of cross-model ID using Wi-Fi for dual person identification from candidate video footage by Bilal Coroni et al. And IMWUT automatic extraction of virtual on-body accelerometry from video to for human activity recognition by Qual et al. And I want to learn how to scale wireless data from almost unlimited data sources like videos. So in a nutshell, the main idea of this paper is to simulate RF measurements to train a neural network and then test it directly in a real-world environment for human active recognition, or HAR, for abbreviation. With focus on dream activities. So in the literature, most of the state-of-the-art systems are learning-based. However, the two main drawbacks include collecting. So the first one would be collecting RF data is labor intensive, and the second one would be once trained, it's hard to generalize or transfer to a different environment. Therefore, so what these authors in this paper propose is to generate human motion-related RF measurements from large-scale data such as videos without collecting real RF data. And they claim it to be a generalizable and scalable framework. So now let's go to the pipeline. The details of the pipeline are shown in the bottom. So what we should know here at this point is that, well, the goal is to perform HAR without collecting RF in the real world, shown in this top graph, right? So in order to remove the need for RF collection in the real world, the authors propose to exploit the unlimited publicly available videos on the internet. And the question is, can we generate wireless data from these videos directly and then construct a massive simulated RF data set? So to that end, one needs to model the key elements of RF for HAR, including modeling RF signals and more importantly, how they reflect the human body surface and the environment, and eventually captured by RF receivers. So in order to which is here, then in order to simulate RF reflection of the human body, then the question is how to model human body, right? So especially the outer surface. To that end, the authors reconstruct a 3D human mesh from the video and from videos, and then shows. So here we see two examples of a person doing jumping jacks on the left, and the person doing step leg deadlifts on the right. So there are points in the mesh 3D vertices and the local coordinate system, or LCS for short, defined with respect to human body, where X points to the front of the person, the Y points to the person's left, and Z-axis points upward. So specifically, the authors use human mesh recovery algorithms for HMR for revision. And the only thing that we need to know at this point is that it takes an image as input and regresses the property of camera. So so property of camera parameters, such rotation, translation, and human body shape, beta, and pose theta. The end result of human body 3 points in the camera. The end result would be human body 3 points. The camera coordinate system. Then, in order to generate a mesh, so the next step is to use a skinned. Let's go over here. Oh, it's actually here. So skinned multi-person linear. Or you could just call it a SMPL model proposed by Lauper et al., where the details can be found in this paper. So what we should focus is the ability to translate the infrared body pose and shape information, beta and theta. There's beta and theta into human mesh. So an SMPL human mesh is a set of triangulated points in 3D space describing the body surface. More specifically, the structured 3D human mesh is characterized by a dense set of mesh points that describe the body surface in 3D. So formally, formally, the set of 3 points of the extracted human mesh at time t is defined as n prime t, where p prime m of t is the 3D location of the m point at time t, and m is to the number of points in the mesh. Note that these points are given in a coordinate system where the xy plane is parallel to xy plane is parallel to the camera plane. In addition, the authors define a local coordinate system (LC) with respect to the human body, where I think I mentioned that. So what we are more interested are the coordinates of these points in a GSC, global coordinate system, because in GSC, we do not need to worry about coordinate frame transformation. However, what's missing here is the rotation matrix. Right. So then the question is how to find the rotation matrix. So what's next? The next step is trying to do, which is to align LSC to GSC. So observe that in LSC, axis actually is defined as the same as the human body orientation, meaning that if we are able to identify the x prime in the original coordinate system, we already know the rotation matrix here. So now here, imagine we have some point of a flat plane in coordinate system. It would be trivial to figure out the normal of that plane. So, and with that intuition, our torso, the central flat part of our body acts like this plane. Now, now that we have a 3 by empty matrix of the 3 locations of all the massive points belonging to the torso in the original coordinate system. If we imagine this is 3 points, right? So if we run eigenanalysis on these points, then the smallest eigenvalue would represent the anterior, posterior, the front, back direction, which will be the x prime axis in LC, while the largest eigenvalue would indicating the interior, superior, and bottom up is the z prime axis, meaning that we have already found the solution of the problem. So at this point, we are able to model the outer surface of human body parts from videos, which is the preparation for modeling RF reflection of the body in order to do human activity recognition, which is the final goal. The next, then the next step is to simulate RF signals shown in this pipeline. Let's define PT. Here. So PT and PR are the locations of the RF transmitter and receiver in the GSC. So the received electric field at the RX which is EPR, due to a transmission from TX, is the solution to the volume integral equation here. And then, so what D is the workspace where the transceivers and the person are located. The Green's function is denoted as G, which encodes the dynamics into partial differential equations that describe how a field responds to a source for that field. Lambda is the wavelength of the wireless signal, and O of P is the parameter that captures the electric magnetic property of what resides at position P in the area. So several methods have been proposed for finding the solution, such as methods of moment, MOM, and the finite element methods, FEM, whose details can be found in in the reference papers. However, to compute this, it's very intensive. So here, because we have 3 in the group here, 3 orders, and to alleviate this problem, oh sorry, here, EFP. So to alleviate this problem, point approximation is proposed by Zhou et al., which treats each point in space as an independent scatterer and does not take into account the higher order scattering effect. So here we see E of PR, original E of PR equals something here. So another E is nested into this equation, which means that this one depends on the calculation of this one and so forth. There's a loop here, which makes the computation expensive. Then when we do the point approximation here, we just treat it as an independent. So each point is just treated as an independent scatterer. Scatterer of the second scatterer, which means that one E of PR does not depend on there's no in loop for to calculate E here. So just we just calculate here directly for this E. Then now that we have introduced the RF signal, so here's the RF signal wave propagation modeling. So the next step, the authors focus on the case study of 10 gene activities, including broad jump, forward lunge, and so on. They collected a training video dataset from YouTube consisting of 61 videos of gene activities, each of which containing an average of 8.39 seconds of relevant activity content. Okay, the point here is that they use only Wi-Fi CSI magnitude measurements of small number of links. No. The point here is that they use lots of training data from free from YouTube. And then here is here's the RF transceiver placement. Just to be concrete, so they use 3 Wi-Fi links to capture the velocity components of different body parts along 3 dimensions, where the coordinate system is marked as follows. The person is located at the origin, facing the positive X direction and the positive Z direction is pointing upward, similar to the one I mentioned. So each link is a pair of transmitter TX and receiver RX. So for example, link one is here. So link one is placed in front of the person and parallel. So link one is parallel to the y-axis. Link 2 is parallel to the x-axis. And link 3 is actually on top of this one, is parallel to the y, but it's an opposite. Yeah. Then formally, the baseband Wi-Fi signal received by RF of I link can be approximated as follows. So where I is the directional from the direct signal from the TX to the RX of the I link, and RSI is the signal of static path reflected of the static object in the environment, and alpha n is the amplitude of the reflected path of the nth body path. The N of T is the 3D velocity vector of the nth body part at time t. And Li is a unit vector bisecting the angle between the two lines connecting the nth body part to the tx and x of the ith link. And lambda is the wavelength of the RF signal. So the squared signal magnitude can be written as this one. If you do the math, eventually you get these. So know that the frequency term. So P is the DC component of this one. Now the beauty of this setup is that so we can, as you go, so the frequency content of the received signals at link 3 will directly capture the velocity components of different body paths along the x, y, and z direction respectively. As such, the received signals at the links contain key information on the person's 3D motion profile, which will be useful for classification tests. So I've introduced the test, we can move on to activity. So in order to do Wi-Fi based dream activity classification, they further divide each activity into segments of repetition, where a repetition is defined as one complete movement cycle, and atomic unit of a dream activity, such as a cycle of one push down and up as one repetition of push-up activity. To determine the period of each repetition, the authors first employ mass CNN to extract the bounding process of the person, and then check the periodicity by the aspect ratio of the bounding process among the video. Then we do the same steps presented in the previous slides that extract 3D mesh of the person doing the activity from the video, who is placed and oriented in the GSC, as well as the Wi-Fi signal, Wi-Fi transceivers, and in the locations described, where the TX-RF separation distances for links 1 and 2 are 2 meters each, and the TX-RF distance for link 3 is 0.6 meters. The antennas of link 1 and 2 are placed at 0.75 meter depth of the floor, and the antennas for link 3 are placed at 2.75 meters above the floor. Now, given the location of the M3D mesh points in the GSC in the video, we can simulate the received Wi-Fi signal as follows, where P, the R and PT are the location of the RX and TX respectively. PM of T is the location of the M mesh point at time T. AM is the reflection coefficient of the M mesh point, and GM is a scaling parameter that captures the quasi-specular reflection nature of the human body and depends on the normal direction to the body at the M mesh point. Then when a person is doing some activity and signals reflects off human body parts, and because of this filling setup, each receiver captures the information on speed and direction of movements. So for instance, the up-down movement of the person's body parts can result in speed in the Z direction, right? And that there's no speed in the XY direction. while a high speed can be captured in the excess when doing a broad jump. So therefore, the feature of gym activity classification is based on this velocity profile that includes the information of the speed and motion direction of human body parts. To capture the velocity profile, a common method is time frequency analysis, which transforms the received signal into the Fourier domain. The frequency domain to that end, they use short time Fourier transform with windows of size 0.4 second and a window overlap of 0.35 seconds to generate a spectrogram, which contains the frequency content of signal. So in the range of 1 to 100 hertz. Also, to remove noise, they zero out all the spectrogram values that are below a noise floor of 0.01. Now, given the spectrograms of each repetition, feature for classification is based on the quantile of a spectrogram. In particular, the Q quantile of a spectrogram S of F and T is given as follows as a function of time. So where Q is the Q quantile of the spectrogram as a function of time, and F max is the upbound of the frequency in the spectrogram, which is 100 hertz in our case. So the intuition behind this equation is that it robustly captures the temporal variations of spectrogram, which captures the time varying speeds of each body part. Specifically, so the authors use is 0.5 and 0.7 quantiles for each spectrogram, which capture the medium speed and high speed components of the motion over time, respectively. And here's an example of what the spectrogram and the 0.5 quantile distribution of the stiff leg deadlift exercise in link 3 shown in figure P and C. Recall that link 3 is placed above the person. So we can see that when a person's main body moves up, it results in the increase of frequency from T1 to T2 and T1 and T2. So in the end, we will have 33 features in each representation. We calculate the histograms of 0.5 quantile and the 0.7 quantile in a 5-dimensional vector in the following intervals. So 1 to 10 hertz, 10 to 20 hertz, 20 to 30 hertz, 30 to 40 hertz, and 40 to 100 hertz. In addition, to capture any possible temporal asymmetric within one reposition of activity, they calculate the difference between maximum value of the quantum values in the first and second halves of the repetition by using a binary number to indicate whether the difference is larger than 10 hertz. And for each quantile curves of link 3. So after training a classifier based on these features, they test the gene activity classification system in the real-world environment of the lab. A classroom and a conference room shown in this picture. They recruited a total of 10 subjects to participate in their test experiments. So to evaluate the system, one important metric is the similarity between simulated and real Wi-Fi signals. So here's the visualization on 2 links for 4 exercises, stiff leg dead rate. So forward lunge, B and C, lateral lunge, and D broad jump. For each exercise, left figure is the real RF spectrogram visualized here, and the right one is and the middle figure is the simulated visualization of Wi-Fi spectrogram, and the right figure is extracted 0.5 quantiles from the two spectrogram. The average cosine similarity between the 0.5 quantile curves of the simulated and real spectrograms of 4 activities is 0.88. And the authors wanted to emphasize that the advantage of the simulated RF data. And here is the summary of activity classification results, indicating the confusion matrix of 10 gene activities based on individual repetitions of the activities, as well as the classification accuracy. Overall, it achieves an average classification accuracy of 81%. The main errors are due to the inherent similarity of gene activities such as lateral squat jump and lateral lunge. Since this is computed on each repetition independently, when considering the average of 5.1 repetitions each, we see an improvement on the classification accuracy. So another key observation is that it is robust to metallic objects in the environment, highlighted in green, which can result in static multiplier. I recall that in practice, the direct path from the TX to RF is stronger than all refract path. So the figure shows the spectrograms of the received wave signals in both settings for sample exercises, and the spectrograms of the received signals are almost identical. Then this concludes this presentation. So the authors propose the generalizable and scalable framework that uses unlimited online video as to generate RF data and to test on real world without collecting real RF measurements. Okay, see you next week.